In our first chapter, we were just focusing on a motion with constant speed or constant velocity. What does this mean? It means that you had no acceleration whatsoever. Right now, on this chapter, we are going to consider situations in which you do have acceleration. This acceleration is going to be constant. You don't have to worry about varying accelerations, at least for now. It's going to be a chapter later on the syllabus. Right now, you have to focus on situations in which the acceleration is constant, and this means that the speed is going to change linearly, basically always at the same rate. But let's look at what acceleration is in the first place. You already know from previous years that the acceleration measures the rate of change of velocity. Velocity, not speed. Although here in mechanics, you use indistinguishably velocity and speed because you only have situations in which these two are going to happen. Either an object speeding up or an object slowing down. You know that you can also have situations in which the speed is not changing, but you still have acceleration because the direction is changing. And since this is a vector, this is all you need in order for you to have an acceleration. So you have acceleration every time something speeds up, slows down, or turns. You don't have to worry about this last one. In mechanics, if you have physics, you will have to deal with this. Mathematically speaking, what is the acceleration? That's basically the change of velocity over time. We are going to use these letters in mechanics. V for the final velocity, U for the initial velocity, T for the time, and A for the acceleration. The international system units is meters per second square, but you may have questions in which you may have, for example, kilometers per hour squared. It is assumed that you know how to convert one into the other. In relation to motion graphs, everything that you learned in the last chapter about displacement time graphs and speed time graphs is still valid over here, namely that in order for you to determine the velocity out of a displacement time graph, you have to get the gradient, but now you won't have a straight line up, you will have a curve, all right? So how do you get the gradient out of a curve? How do you get the velocity at a specific moment in time? You have a curve, so you don't know how to get, it is impossible for you to get the gradient of a curve. So what you have to do, you have to draw first a tangent, all right? On that point, draw a tangent, a line that touches the curve on that point only, and you get the gradient of that tangent. Pick 2 points on that tangent that are as far apart as possible. You should draw the triangle, all right, connecting these two points. Then measure the height, measure the distance, divide the first by the second, and that's going to be the acceleration. What about velocity time graphs? With the velocity time graph, just like in the previous chapter, you can calculate the distance by calculating areas, right? But now you won't have straight lines like you had in the previous chapter. Previous chapter, constant speed, so you would have straight horizontal lines. Now you have acceleration, so you will have lines with gradients, either positive or negative, either with objects speeding up or slowing down. But you can still calculate the displacement by calculating the area, but now you'll have shapes like this one, a trapezium. Don't forget the area of a trapezium. It's always, in a trapezium, you will always have two sides that are parallel, one tinier, one bigger, and the formula is the smaller side plus the biggest side, altogether, the whole thing multiplied by the distance between them, divided by 2. More on that later in our next lesson. No, actually on this one. So you can calculate the displacement, calculating these areas, and you can calculate also the acceleration now. That is something that you didn't need to worry on our previous chapter, as you had constant speed, so the acceleration is always 0. But right now, you will have acceleration, which is basically calculated using the gradient of these lines. The higher the inclination, the higher the gradient, the higher the acceleration, because the acceleration is the gradient. Look at what the gradient is. the gradient of this line is this change in velocity, right? The change in height over the change in distance. So a change in velocity over a change in time. And that is the definition of acceleration, right? What if you have a curved graph? If in the unlikely event that you have a curved graph, then the acceleration can be calculated the same way as you calculate velocities on a displacement time graph right now. You have to draw first a tangent, pick 2 points, draw the triangle, change of height over change of distance. That's your acceleration. You can also you can also estimate the displacement when you have curved graphs. What do? You try to figure out the best possible regularly shaped object that can be fit inside this curve, determine the area of that, and then by comparison, see what you have left behind and make your best educated guess of how much this area is and add to the value that you have there, that you calculated there. All right? This is called an estimation and not a calculation. All right? Obviously, in mark schemes, you will have a range of values that they would accept for this. Let's see an example. Let's say that you have a graph like this. Again, I did this by hand. These are supposed to be straight lines, all right? So there's a lot you can see from this. Your best friend in this type of questions is a velocity time graph because you have all the information that you need, assuming that you have numbers on the velocity scale and on the time scale. Why is that? Because the velocity at any given moment is given by the graph itself. The displacement is given by the areas, and the acceleration is given by the gradients. So everything is here on a velocity time graph. Again, how do you get the areas? Is the shapes that you have between the line and the x-axis. So this area over here, this triangle, is going to be the displacement from 0 to 5 seconds. All right, so 5 times 5 divided by 2. Here you will have a trapezium. Okay, look, identify the two sides that are parallel is this and this. I'm talking about this shade here in the orange. So the area of the trapezium is smallest side plus biggest side. So 5 times 10 times the distance between them, which is 5 minus 7, 2, divided by 2, so 15. If you forget the formula for the trapezium, you divide this into sections, a rectangle and a triangle, calculate the area of each and add them together. But I usually advise you to just memorize the formula for the trapezium because it speeds up everything a lot. Area of this one is just a rectangle, so this is 15 minus 7, which is 8 times 10, 80 meters. Same thing over there. Over here, you have this area that is on the negative side of the velocity, below the time axis. So this is 5 times minus 5 divided by 2, so minus 12.14. Now, would you put the minus or not? It depends on what the question is asking. If the question is asking for the displacement, you have to use the minus, right? Don't forget, this is a vector. So the total displacement, for example, in this question, it's this plus this plus this plus this minus that. All right, so it's a total of 120 meters. But the total distance is not. All right, the total distance you keep adding. The direction doesn't matter. Doesn't matter that in this case is already going backwards in relation to what you consider to be the positive direction. The distance traveled is added over here. So the total distance traveled here is 145 meters. The acceleration is the gradients that you get there, all right? The gradient of this one, so 5 divided by 5, it's 1 meter per second. The gradient of this one is 10 minus 5 divided by 2. So, where is it? 2.5 meters per second. Obviously here, the gradient of a straight horizontal line is 0. And so forth. These are negative gradients. And that's all that you need to know in terms of graphs. It's now time to figure out how to make calculations that are analytical in nature, and that's the purpose of our second lesson.